learning, which is a subfield of AI, and lots of deep learning methodologies are developed for computer vision. So by computer vision, it means how you can get the computer to analyze the images similar to how humans analyze these images. So it has lots of applications like face recognition, fingerprint recognition, and even medical image analysis. So it's a very interesting topic, and I suppose most of you wouldn't really have any knowledge in computer vision. So I'm scoping the content to be mostly at the AI side. So it wouldn't involve lots of understanding about computer vision, but I will still need to cover quite some content in computer vision in order for you to actually understand these applications. So I will keep this introduction to the intuitive level, and I will just focus on the most popular algorithms. So actually, has any of you taken the computer vision course? No? So, okay, that's good. So I will just try to cover those contents as intuitive as possible. But if you do have some questions throughout the lecture, especially during the second half of the lecture, I will need to talk a bit more about computer vision. So if you have any questions, just let me know, or you can just email me after this lecture. So, okay, so that's the outline of today's lecture. I will start with some introduction of applications of AI in computer vision, and then I will introduce an overall framework, the essential components, how you can develop a computer vision application. So I will use handwritten digital recognition as a case study throughout the first hour of this lecture. And then from the second hour, I will move on to some more advanced topics like texture classification and AI in biomedical imaging. And throughout this lecture, I will also give you some reference readings for you to read after this lecture, because I will need to cover quite some content, and it will be mainly the high-level understanding. So if you want to do a deeper study and get more broader knowledge, you can just refer to the reference readings, or you can just search online. There are lots of materials out there. So as an introduction, AI has many applications. So we all know now it's almost talked about everywhere, how AI can be used in medicine, robotics, finance, transportation, and even arts. People are talking about using AI to generate really interesting artworks. So it's a very interesting topic. And many new trends of AI technologies are developing computer vision applications, like face recognition or surveillance, remote sensing. So, here are some images. This is an example of face recognition. So face recognition is about you want the computer to detect which person this is, regardless of changes in like hairstyle or the background or the lighting, and the computers should still recognize who this person is. And it has lots of applications like security control, or if you go through the border security, now there's a system to recognize who you are. So it's a very active area in both industry and even research as well. Even after maybe 30 years of study in face recognition, it's still a very popular topic now, because the researchers are dealing with more and more difficult problems. So, and especially now with deep learning, there are different ways of doing face recognition. It's not just algorithms anymore, but learning-based. So more and more AI approaches are developed, and also for this example, it's a surveillance. So if you have a camera recording at the train station, and if someone just fall into the train track, you would want to have this alarm as soon as possible. So that's where computer vision comes in. You wouldn't just want to rely on someone human to look at the surveillance camera all the time, but we would like to have a computer to do this detection as quick as possible. So, so that's just some brief introduction about why we want to study computer vision with AI-based techniques. And so in this lecture, I will cover some overall introduction about the main components of computer vision framework. So, so there are lots of ways of doing computer vision, but if you consider a subfield of AI, then I think most of you are very interested in deep learning. So machine learning is kind of the superset of deep learning. And that will be the most important component in a computer vision application. It's about how you want to do learning-based classification. And then so when you actually think about doing this application development, you need to design a machine learning algorithm to classify the input data. So that's the most important component in the modern computer vision frameworks. So that will be also the topic of this first hour of lecture. And then from the second hour onwards, I will move on to talk more about feature extraction, which is the essential problem of computer vision. And it also involves lots of learning-based techniques. And if you consider deep learning, it can be a kind of feature extraction technique. So that's the second main component. And then also evaluation is always important. In any kind of applications, you want to have some scientific way of evaluating the systems. So I will describe some ways of evaluating the performance. Okay, so machine learning will be the main topic of this first hour, and essentially it's a subfield of AI. So AI has lots of algorithms. You have learned about the gaming theories, maybe also genetic algorithms. And so machine learning is a subfield of AI, and it provides the system the ability to automatically learn and improve from experience without being programmed explicitly. So if you look at this figure, it's a very good high-level view of what machine learning is. So essentially, so with machine learning, the objective here is we want to learn a model that can do prediction of the data. And with this model, we are able to improve the performance of the system compared to what you would do with explicit programming of certain type of algorithms. So for example, if consider medical image diagnosis. So if there's a patient with some conditions, then of course the patient will do certain type of tests like blood tests and maybe some medical imaging like MRI or CT. And then the patient gets all the data from those diagnoses. And then the doctor will predict whether the patient has certain type of disease like cancer, or if this patient does have cancer, then maybe the doctor wants to decide whether the patient has a 5-year survival rate. So all of those tests, those medical tests, the images and blood tests, are kind of data associated with this patient. And then whether the patient has certain type of disease or he's able to survive, we can consider it as the label associated with the data. So if we have lots of patients that has been diagnosed and they have gone through those treatment process, and we know whether those patients have survived the 5 years, so we can generate this data set as a training set. So we can have some data associated with these patients, and then we also have the ground truth label for all the patients. So that's a kind of is what is mentioned here is from the experience we got those training set. And then from this training set, we can just design a machine learning model. For example, you've learned neural network. So we can use neural network as the machine learning model, and then we just train it using this data. And then we would get a neural network model that's able to do this classification based on the patient data and get a prediction of whether the patient can survive 5 years, for example. So that's the idea of how you do machine learning. You wouldn't want to do a conventional programming-based approach. So for example, if you consider standard programming, you might consider just do if-else switch statements. If the patient meets certain type of conditions, you say whether the patient can survive 5 years, else then some other conclusions. So machine learning is totally different. There's no logical manipulation based on those data, but it's all a mathematical model that can be trained using this training set. So that's a very brief overview of what machine learning is. So, so here in this course, I wouldn't really go into the theories or fundamentals of machine learning. So if you're interested, you can always look up online. There's very good free online courses out there. But in this course, in this lecture, I will just give you a very practical view of how you can actually develop those applications using machine learning for computer vision studies. So I will use handwritten digit recognition as a case study here because handwritten digit recognition is essentially the simplest problem in computer vision. And it's also a very classical problem that has been done for 30 years. And many technologies have been developed based on handwritten digit recognition. Even the first deep learning approach was developed for handwritten digit recognition. So it's a very good entry point for you to understand both machine learning and computer vision. And also with handwritten digit recognition, you can just use the whole image as the input data. So you wouldn't need to do some image processing, very complicated image processing or computer vision manipulations. So it's pretty independent of the feature extraction component, and we can just focus on the machine learning aspect of this, this problem. So, in the first hour, I will go through what are the typical ways of implementing a machine learning method, and some overview of very popular classifier models. That means machine learning models. So for example, the neural network you have learned a few weeks ago. So that is kind of classifier model, but there are some extensions based on the basic feed-forward neural network. So I will go through those extended models. And then I will also give you some resources for further study. So what is handwritten digit recognition? Is essentially like what you see here. So here are 8 individual images. So each image has 1 digit, and the digit is handwritten. So it can be any type of fonts, depends on how the individual writes those digits. So the idea here is we want to have the program to be able to classify what is what this digit is automatically. So each image here is black and white. The digit are white, and the background is totally black. So it's a very simple, actually it's a very simple computer vision problem, because you wouldn't be concerning about the noise introduced by the background. So we can go to this link and just, I hope it works. Okay. So what you can do here is you can just use your mouse and draw a figure. Like, does that work? Okay, so it doesn't really work. Okay, so essentially, this one is it's a very good tool. It has two boxes. So on the left box, you should be able to just use your mouse and draw a number. You can draw it pretty. You don't need to draw a very good written number. Can be quite strange. You can make the numbers really not the normal way of writing, but it will still detect what this digit is. This system is quite accurate. If you put 1 here, it will display the digit number 1 here. So you can try it after this lecture. It's quite interesting, and you can try whether you can think of some ways to make it give you a false classification result. It can be quite challenging because this system is quite robust. Because it's been 30 years of research, and nowadays I think the accuracy is close to 0.2% of error rate. So it means it will be very accurate. So, okay, let's go back to this. So there's lots of applications in the industry. The first approach was proposed for reading the postcodes written on the letters, because many years ago people still use handwritten, the handwriting way of posting letters. So it was very useful at that time, but now it's becoming the industry standard to use some kind of neural networks to do this handwritten digit recognition for letters. And then the other application is we can have a bank check, automatic reading of the numbers written on the bank check. And so if you think of ways to do this, one way is assume you just don't know anything about machine learning, but I suppose you would still think of some way that can be quite intuitive. For example, if we know a set of digits, we can call those as the templates. So for each digit, we can create a number of templates based on, you can just use your Word document to have those different fonts of numbers. Then you would have a set of templates as the training set, for example. And then if you have a test image too, then you can just match between the test image and the set of templates. So here you can just do pairwise matching. That means you can just match this test image with the individual template here one by one. And once you match all of those, then you can choose which one is the closest to the test image. For example, this one might appear the most similar one. Then we say this image is the same digit as this template, because we know beforehand what are those digits are of those templates. So if this one match with this one, then we can conclude this one is 2. So that is kind of the k-nearest neighbor classification approach. So nearest neighbor means the most similar images, because in computer vision, we always like to consider images as some kind of graph. So we use lots of graph-related terms to name those algorithms. So if you just check the top one most similar image, then that is called one nearest neighbor, because we only consider one image, and that is one nearest neighbor. But most of the time, one nearest neighbor wouldn't give you a very accurate result. So you can just increase the value of k. So if you use 3 nearest neighbors, then we just find which are the top 3 most similar images. So in this case, for example, if the top 3 similar images are these 3, then 2 of them are 2. So we just use a majority voting kind of technique to say, since majority of this give you a 2, so the test image will be 2. So that is what k-nearest neighbor does. And so with this very simple approach, 3 nearest neighbors, we can get a 5% accurate error rate. So that means 95% accuracy. And one thing I hope you understand a bit more is so how you can actually match this image with those images. So because they are images, you can consider them as a matrix. And when you do the matching, it's essentially just compute the difference between 2 matrices. So, so that is just element by element difference, and you can just compute the difference between each element, and then you sum those differences in the matrix, and then you get the overall difference. So that's a simple way of doing distance computation between matrices, and that is called Euclidean distance. So if you still remember your linear algebra, so that is the Euclidean distance, and it's normally the standard way of doing distance computation for images. But there are also many other ways, and you can even do learning-based ways to do this distance computation. And if you are interested, you can just search online for distance metric learning, and that will give you lots of information about how you can use AI machine learning-based technique for distance computation. So that's one way. I think that's the most intuitive solution for finding the handwritten digit recognition. And that example actually gives you an overall view of the framework used in computer vision. Essentially, it has 4 steps. The first one is we construct a database for training. So in this example, these templates will be the database for training. So we just call them the training data. And I'm just showing you this size of images is not too many, but in practice, you want to have a much larger data set for training. And normally we consider the larger the data set is, then the more robust you can get a computer vision, a machine learning model. And then the second step is image pre-processing. So here, we will definitely do some image pre-processing if you want to do like the bank check reading. Because when you write the bank check, what you get is an image of lots of digits and some other words. And you can't just use the whole image to do processing. You have to just detect all the individual digits and separate those digits. And then you want to make the digits black and white as a single image. And also all the images in the training set are also one image contain only one digit. And in that way, you can do this matching-based approach. So you have to make sure that your test image is as close as possible to the training image. So then your method can be more robust. If they are very different, you wouldn't expect a very good application result. So that will be some simple image pre-processing techniques involved. And then the third step is the most essential one. We want to create a machine learning model. So here, in this example, the machine learning model is this k nearest neighbor. And normally you would want to try a few options. So for example, you can try 1 nearest neighbor, 3 nearest neighbor, or even 5 nearest neighbors, and see which one works best. And that will be your machine learning model. And then finally, once you have this test image, you can just apply the machine learning model that you have trained on this test image, and then you can get the result, what the number says is 2 in that case. So, so just to try to help you to understand a bit more about this overall framework, there's another example of using a different type of machine learning model. Just go through this framework again to illustrate what are the 4 steps. So this is based on pretty old work, but it's really the classical approach. And I think everybody interested in machine learning or deep learning and computer vision should know about this work. So that's why I'm including it here. It's based on the backpropagation network. So a backpropagation network is essentially the same as neural network that you have learned a few weeks ago. So, but it's a more extended version or more complicated version than the standard feed-forward neural network. So I will go to that later. But the first step is we want to create a database. So in this study, they have generated a database that has a large number of images. And to get those images, they considered getting images from handwritten postcodes. So those are the real images they get from the post offices, how people really write those postcodes in reality. And they get this number of images, and each image has only 1 single digit. And then they also get another set of images from printed digits, but of different fonts. So this data set is quite big, and it has lots of varieties in the images. To make sure that you would want to cover as much diversity as possible in your images. So in that way, when you are given a test image, it becomes more likely that the test image actually resembles some set of the training images. So that will help a lot in your application. And then they divide these images into 2 sets. The first set is the training set, and the second set is the test set. So the training set has more images than the test set. That's the normal way of doing it. You would want to have as many images as possible in your training set. Then you would run into less overfitting problems, and you can generate a more robust machine learning model. So, when they do training, they will use this training set to generate the machine learning model, and then when they do testing, only the test set is used. So there's a clear separation between these 2 sets in order to ensure that you don't want to get fake accuracy, because you would be testing using your training set, for example. That would be a not good practice. So, so something quite important here I want to just have you keep in your mind is both sets contain numerous examples that are ambiguous, unclassifiable, or even misclassified. So that means, for example, the images would contain digits from these images. So if you look at this number, 96203, I think, or someone might consider it as 5. So it can be quite ambiguous to different people. And so if you use this image as the training set, so it means your training set might not be perfect. So it means some of the ground truth labels might not be accurate. And those inaccuracy would affect the machine learning model, the accuracy of the machine learning model. And some of the numbers might be even unclassifiable. So when you do the testing, no matter what the number you get, the accuracy you count might not be real reflection of the actual performance. So these kind of issues are just prevalent in any kind of applications. So you might not really feel the importance right now, but if later you do some study in this area, I think you will want to consider this point. It's actually a very important and very realistic problem in any kind of methods you would want to develop. So then that's the second step. That's still the same as the previous approach. You just want to do some simple pre-processing techniques for these images. And most importantly, we want to make sure each image has only a single digit. And so if they write the digits continuously, and you have to divide those numbers into separate images. And then we want to normalize the size of the images. So it means all the images should have the same size. And that's important for the machine learning model. So the third step is to create this machine learning model. And in this method, it's called a multi-layer neural network. And it's very similar to a feed-forward neural network, but it's only first a few layers involve these convolutional filters. So if you heard anything about deep learning, it's essentially all about convolutional neural network. So convolutional means some of the layers in the neural network would involve convolutional filters. So in a standard feed-forward neural network, you would just have some neurons that have weights, and then you just multiply the previous layer with these weights, and then you do a summation to get this output. So those kind of processing is not convolution. So convolution is the standard way what you've learned in convolution. You would have a filter that has a very small size, and that the filter can go through this whole image to do this convolution over the image. And then, so with convolution, the most important benefit is we can reduce the size of the neurons. So if you use feed-forward neural network to process this kind of images, you would need lots of neurons to get meaningful outputs. But with convolution, you can just have very small filters. And so first of all, with small filters, you can get fast computation and also reduces the memory requirement. But also with convolution, the best advantage is it actually does all this processing locally on certain regions of the images. So it doesn't process the overall information in the whole image, but it goes through local regions. So that is the main idea of convolutional neural network. So, but here, this model is not really convolutional neural network. It's still missing lots of components in nowadays convolutional neural network. It doesn't have a fully connected layer or those kind of activation functions. So, but it's the very first, you can consider it as the very first prototype of convolutional neural network. So many years later, people start to name it the LearnNet1 because essentially the first CNN is LearnNet5, but this one is the first prototype, so it's LearnNet1. And it's a pretty simple idea, but it does work really well on this kind of images. So once you train this network, and then you can get error rate of 3.4%. So it's slightly better than the KN approach, but it does give you a different way of processing these images because it is really a generic model that can be applied to any kind of images. So even this type of images, this network can detect those digits accurately. So, so just a recap of what I have tried to talk about previously. So to design a machine learning system, the most important thing is we need to construct a training set and a testing set. And you need to make sure you have sufficient diversity and quantity in the training set. Then that will help you a lot with training the machine learning model. And then the second component is you want to train the machine learning or classifier model, and then later you can apply this to the test images. And in this process, most of the time you would need to do some image pre-processing. That will be dependent on the types of images or application domains you want to work on. So, but most of the time it's quite simple image pre-processing. And then, so based on those initial techniques, the KN and the LearnNet1, there's some further study on this handwritten digit recognition. And probably the most important milestone is some years later, the same group of researchers, they create a very big database. It's called Minutes database. And the training set now has 60K samples, and the test set has 10K samples. So with this large size of database, it enables many subsequent studies of more advanced methodologies. So because with any type of machine learning model, you do need a very large database. And so with lots of images, you are able to cover lots of situations or scenarios with those images. And if later on you do study machine learning, you would hear lots of talking about overfitting. So that is some kind of issue with you try to train the model, but with a very small number of data. But if your model is very complicated, then you would run into this overfitting problem. So large set of data is very important. And then with more studies, people start to develop other machine learning models for this area. And we can roughly categorize them into linear classifier, nonlinear classifier, KN, SVM, and CN. That's the deep learning approaches. And so I will not really talk into these models. If you are, I think many of you would consider taking the machine learning course, then you will learn a lot about these models. especially support vector machine. It's very successful and very popular in many areas. Even now, with deep learning, you can do integration of deep learning with SVM in many applications. So it's and the idea here about SVM is actually quite elegant. So so I will just talk a bit more about KNN. So the K nearest neighbor. Remember that if we just use 3 nearest neighbor with direct computation of distances, we can get 5% accuracy error rate. So, but with another approach, about 10 years ago, and you can get the error rate down to just 0.52%. And that is very good. Consider we just use a very simple machine learning model by just matching between images. But here, the difference is we want to make the image processing side of algorithm more complicated. So that means we can, so when you compare the 2 images, you're just not using the original images as the input. So, but you do another step here. You can just deform those images a little bit. So for example, if that's one image, and then that's the, this 6 might be the template image, and this one is the test image. So if you want to consider what's the similarity between these 2 images, you can just deform this number towards the template first. So by deformation, I mean you can just shift those pixels around in the matrix. And here, these figures show you the deformation field. So the curves mean how you can just move those pixels in certain directions, and then you will get a different image here. So the test image will look quite similar. After deformation, the test image will look quite similar to the template image. That's different types of deformation. So once they look more similar, then you can do this subtraction between the 2 images to get the distance, and that will be used in the KNN classification. So, and the other case is if the test image is actually 5, but you still do this deformation, but so the test image will look more similar to 6, but still it wouldn't be as similar as this real 6. So you still can tell the difference. So this one would be more different from 6, and this one is more similar to 6. So in this way, they actually managed to have a more accurate classification. And so that error rate is pretty good. And then another trend of study is to improve the neural network model. And then that's when the first convolutional neural network appeared and was designed for handwritten digit recognition. And so that is called LeNet5. It's pretty similar to the LeNet1, but here is a complete convolutional neural network model. Means besides the convolutional layers, now we also have these subsampling layers. So it means gradually, while you do these convolutions, you're actually reducing the size of the output smaller and smaller. So from this image size, you're reducing it to something like this at a later layer. And then you can also append fully connected layers. The fully connection is the same as the feed-forward neural network layers. So just do the multiplication and summation, and then you get this finally you get this output layer. And then you can do some loss function computation. That is for controlling the classification output. So So I'm just giving you a very high-level view of what this convolutional neural network is. I will include a link for your further study if you're interested, or you can just go online and search. There are many good tutorials or online courses out there. So with this approach, they get an error rate of 0.7 percentage. So that is not as accurate as the KNN approach, the deformable KNN approach. But this way is very, you can consider it quite simple because it's just a neural network model. There's no other processing on the images. And you can just dump whatever images you have and just let the network train. And then it's essentially less complicated. But this training process can be quite tuning intensive. So you need to tune lots of parameters in this network model in order to get a really good performing application. So, and nowadays, this system is used to read 10 to 20% of all bank checks in the US. So it's a pretty old model, but it's still used in many areas. And then, so if you look at this LeNet 5, it was developed 20 years ago. But then since then, there was a very long period of hiatus for the deep learning because essentially this network needs lots of computational power to train. And at that time, the computers don't have GPU to do this processing. So the convolutional neural network wasn't really popular in the computer vision domain, and people were still using other ways of computation and other machine learning models to do this processing. So it's only after 2010, roughly around that, GPU was becoming more popular and more available. So then people start to do this convolutional neural network again, and then they got quite lots of success. And so nowadays, pretty much everybody is talking about deep learning. And then during that time, the best performing model was generated. So it's a very simple improvement from LeNet 5. It's just the same as LeNet 5, but adding another dropout layer. So dropout layer is something like this. It's essentially like switches. You want to consider which neurons you want to keep and which neurons you just want to drop out. So that is introducing some randomness into this network model. So the dropout is a random decision. While you train this network, just randomly drop out some neurons. And then with this type of technique, essentially, the network is able to generate an ensemble of a large number of different neural networks. So with this type of technique, actually you are tackling the overfitting problem. So it's a very simple idea, but it works really well and improves the error rate to only 0.21%. So I think ever since then, is pretty much the performance has saturated. So people has moved on to other type of applications and developing more and more complicated neural network models. So that was some other key points I want to just introduce. So when you design a machine learning system, the size and the quality of the training set is very important. So if you want to do some kind of applications, and if you have the freedom to construct this data set, make sure you assemble a very large data set, and the data set should have very good quality. So good quality means it has to have sufficient diversity in the images, and you also want to minimize ambiguity and misclassification problems that I have mentioned before. So, and there are many different choices of classifiers. So SVM, the classical machine learning model, and also the recent convolutional neural networks. And also different classifiers give different performances. That will be, so when you do your development, you will want to try a few different choices of models and see which one performs best. So in some cases, no, not necessarily deep learning will work the best, especially, for example, if you do some bioinformatics applications, you would have a data set that is quite small and has very limited diversity in the data. Then you wouldn't really need deep learning in many cases. So SVM will be probably still the best in many applications. So you will want to try out different choices. So that goes to the summary of this first session. So AI is critical in computer vision applications. And modern computer vision development often requires machine learning or deep learning methodologies. And the same principles, the 4 steps for you to develop those machine learning models, can apply to any application domains. So if you consider financial data processing or even politics, even now politics, they use AI and machine learning to do this prediction of voting. And so many applications, they will use this set of techniques, but with some fine-tuning in the choices. So when you actually design a computer vision application or machine learning model, you would want to consider what are your design choices for all these, the 5 questions. So if you need some pre-processing of your data, most cases you will need some pre-processing, but try to keep it to the minimum so you wouldn't make your system overcomplicated. And then feature representation, I will cover it in the subsequent hour. So it wasn't really an issue for the handwritten digit recognition, but in many other applications, you do need feature representation, the step. So it's more computer vision related, but it also does involve some kind of learning-based algorithms in the feature representation. So, and then the most common one is classifier, meaning the machine learning model, which kind of model you want to use, and what are the training data that's available, and also the evaluation metrics. That can be quite standard for most kind of applications. So in the next hour, I will go to feature representation and evaluation metrics. And these are some further readings for you to consider after this lecture. So the first one is the one, they actually include not just the LearnNet model, but also other machine learning models in that paper. So you can have a read and get some general understanding about all the popular machine learning models. And then a brief summary. This one is very brief. It just gives you a history of all the popular CNN models that's used nowadays. And if you have questions, you can email me. And some other thing I just want to show you. It's very interesting because the MINIS database is like this. It's just black and white. And nowadays, the accuracy has reached 0.21% error rate. So there's not much thing you can do on that database. But there's another new database that's developed. And so this is also for handwritten digit recognition, but it has very complicated background. So even for human eyes to detect those numbers can be a quite challenge. So this is called the MINIS-M database. And so, and also from the method-wise, if you just use all these images with the ground truth model or ground truth labels to do the training, you can still get pretty good accuracy. Now it's 96.5 accuracy. So researchers have been trying to make these problems more interesting that we don't really want to just use these images to do training, but we want to use actually these images, this minis data set, to do the training, and then use that trained model to apply onto this data set, and whether this type of approach can work. And so now, some researchers have got this 91% accuracy, so it's pretty good. But there's still some improvement that can be done. So that's some quite interesting technique. And also with this type of technique, it's not just restricted to handwritten digital recognition. It can be also applied to the style transfer of images. So if you ever heard people trying to simulate the artist's work, so you can just take photo and then you can apply different styles to these photos to make it like oil painting, or it can be the other way around. With a painting, you can make it like photos. So there's some interesting applications. And if you're interested, you can look at this paper. It's it's a very good one. It's not very difficult to read. So that's just for your information. Oh, and I just want to mention that this lecture is not covered in the exam, so it's only for your interest. And so let's take a break, and then I will continue with the feature representation and then the other biomedical imaging parts. Thanks. Okay. Okay, so let's move on to part 2. So part 2 is about texture classification. So this part will involve quite some information about this computer vision side. So it's not just machine learning anymore, because when you do a computer vision study, definitely you do need to have some processing on the image perspective. So it will be quite some content in computer vision. So I hope you can just get some general understanding about this field. And there is another subject on computer vision next term and term 3 as well. So, but here is just for your own interest. So I think it's a very interesting application area. So it's good to know more. And if you are really interested in deep learning, for example, you will definitely want to go into this area and do some experiments or some further study. So, so by texture classification, in short, the objective is we want to classify or recognize different texture patterns automatically. So, for example, in these images, they all show you different textures. So by texture, it means it has a mixture of definition. It's never very standard what texture really is. But if you just consider what you have seen, for example, some fabric has some patterns, and then that's kind of texture. And if, for example, this chair, the cushion seat has that kind of texture so that you can feel. So those are the textures. And here, so all, even the microscopy or images, it has some texture in these images and some circles, and it has very repetitive circle patterns. So that is kind of texture. And then this image, lots of, I think they are pebbles, repetitive and different sizes of pebbles. So overall, this image shows you a texture. And even for your face, you have some texture on your face. And so, so it has quite some applications. For example, in medical images, you can use texture to do diagnosis, especially for microscopy images, because it's essentially about some type of patterns that's present in the image. So normally when we talk about patterns, you can classify them into shape or spatial patterns, so, and even colors. So anything that's not color or shape, you can consider it as a texture pattern. So that is essentially what texture is. And then in one example, you can consider urban planning applications. Nowadays, people use remote sensing to get images from the satellite, and then you can get some really detailed image about the urban environment. And then there are some very important application in urban planning. For example, if you consider the rainforest environment, people want to conserve the rainforest, but you still need to have land for farming. So how do they actually partition the land to have some rainforest, but also some farmland? So that's kind of urban planning problem, and that can be approached by computer vision applications and using the satellite images. And because the image actually captures a really vast area, so you wouldn't want to go into the very minute detail of the images. So you want to just look at overall image appearance, then that becomes a kind of texture classification problem. To say which part is trees, which part are buildings, for example. So it's kind of texture problem. And then another example is for cancer detection. And this one is actually done by Google. If you keep track of the news of deep learning, Google, maybe 2 years ago, they developed this system, and it does really work well with very large microscopic images, and it can really surpass what the pathologist has achieved. So it gives you very accurate, it's still about 70% accuracy, but it does work better than the standard pathologist. So that shows you the power of deep learning in the application of texture classification. So here is this is a GIF image. So the main idea here is I just want to show you how large these images are. So if you go to this is the thumbnail of the image, but you can just keep zooming into the image and then see all the small cells in the images. So this kind of image is called a whole slide image. So if you ever need to do a biopsy, then nowadays people use digital pathology, and then that's kind of the image resolution they can get. It's 40x. Then you can see all the cells very clearly, and even the inside of the cells very clearly. And that's the very important for doing diagnosis for cancer. And then Google is working on this kind of images, but also many other researchers also developing applications for this kind of images. So how do we do texture classification? And then we go back to all these 5 questions that I have listed in the previous session. So, so we do need some pre-processing and then feature representation and classifier, training data, evaluation metrics. So still the same set of questions that we need to consider when we design the applications. So I will start with all those simplest components first. Then I will keep the feature representation to the later part, because that's the more difficult component. So let's start with the evaluation metrics. So there are many types of evaluation metrics you can use to evaluate your system. But the most commonly used one are these 2, precision and recall. So, so if you consider this image, so all those dots represent the data that you have in your test set. So one dot represents one data. And then in your test set, if you consider it's just a classification problem, for example, you just want to classify whether this biopsy represents cancer or not cancer, then that becomes a binary classification problem. So with binary classification, then once you do this classification, you would classify this data into, for example, cancer. Some are cancer, some are not cancer. And if your classification gives you cancer, and they are really cancer, then that's considered the true positive. And if your algorithm tells it's cancer, but it's actually not cancer, then that becomes a false positive. Then the other way around, if it's cancer, but your algorithm didn't detect it, then it becomes false negative. And then, so if it's not cancer and your algorithm says it's not cancer, then that's true negative. So essentially, you get these 4 categories of outputs, and then you just count the number of data falling into each category. And so once you sum all this data result, and you get the true positive, number of true positive, and then also the number of false positive, then you can use true positive divided by true positive plus false positive, then you get this precision result. So precision represents whether your system has detected something that's actually not positive, but your system detects as positive. So you want your system to be precise, so that is called precision. So the higher precision means it's more precise. And then recall means you divide this number of true positives by the total number of all the positives that you have detected. And also not all, all the positives that you should have detected. So that means if you have 100 cases of cancer, but you only detected 50 of them, then you only record 50 from those, 50% from all the data that you should have detected. So then you would want to have a higher recall and also a higher precision. That means you get a good system. And then there are many other ways of doing this evaluation. For example, if you do study bioinformatics, they do talk a lot about ROC curve and those other type of evaluations. But in typical machine learning or deep learning studies, most of the studies will focus on precision and recall. And for classifier, we go back to this set of classifiers that I have mentioned. And so I'm not going to them anymore, and you can get some other information from this article. It gives you a very high level, very condensed view of the popular machine learning models. And for texture classification, we have some standard datasets that you can use. So these 6 are the most widely used datasets, and they are available online. And so anybody can just download them and play around with them. So you can see that they are not very big because texture classification started many years ago, and at that time we don't really see a need of using very large database. So, but then on the other hand, because the data sets are not too large, then you are facing a really critical problem of overfitting when you want to do these machine learning models. And also there are many number of classes in these data sets. Means, for example, for the UIUC database, you will want to classify the 1,000 images into 25 classes. So it's a very difficult problem. So even though it's been studied for many years, but for many of these databases, you can still just reach around 70% accuracy. So it's a much harder problem than the handwritten digit recognition. So just to show you how difficult this problem is, and here are some example images from different datasets. So the idea here is we want to show you the images. They can look very similar across different classes, and within the same class, they can actually look very different. So it's difficult to tell which images belong to the same class and which images belong to different classes. So that is called the intra-class variation and inter-class ambiguity problem. So intra-class means within the same class, and inter-class means between different classes. So for example, here the 3 images in the UIUC database, they belong to the same class, but they actually look quite different. So, and to tell whether these images belong to the same class, you can't use the k nearest neighbor anymore. Because if you just do the Euclidean distance, you will get pretty large distances between these images. So that's not a good way anymore. And another example, if you consider the last row here, especially these 4 images, they can look very similar, but they all belong to different class. I think one of them belongs to paper, and this one is actually sky. And some of them is water, and another one is metal. So they all belong to different classes, but you just really can't tell from these images. So it's a very difficult problem. And that's why in the early studies, people are very interested in using computers to do this analysis, because one of the major arguments is the computer is able to analyze the very fine detail level of structures that we human eyes just can't perceive. So that's a very big advantage of using computers. And lots of the feature representation technique can encode those detailed structure in the image in some very mathematical way. And it's hard for us to interpret how those algorithms actually are doing those encodings, but they do work really well. So feature representation methods evolve over time, and since 1970s, most of the studies at that time were focused on morphological feature representation techniques. So that means you can use lots of filters. If you've ever done DSP, then you know Laplacian transform, Fourier transform, and wavelets. So those are all applicable to images. And you can use those filters to process those images, and then you extract those essentially like edge-like structures from these images, and then you can do some further encoding to get these filter-based features. So those are called morphological feature descriptors. And then later on, people move on to more higher dimensional texture descriptors. So those are very different from the filter-based techniques, and they are more like analyzing the pixels, the intensities, or the relationships between the nearby pixels to get some more in-depth understanding of this texture. Because if you consider texture, it's about repetitive patterns. So if you just analyze localized set of pixels, then you should be able to detect some inherent texture within the images. So there are quite a number of different designs for these high-dimensional texture descriptors, and they are the most popular one prior to the occurrence of deep learning. So even now, many studies have integrated these descriptors with deep learning to get more improved performance. So it means that they can still give you some useful information apart from deep learning. And also at the same time, most of the approaches, they can't just rely on these descriptors. They need to have certain type of encoding technique to represent the whole images. So, and then that is called feature encoding. And I will go into some more detail about these descriptors and the encoding technique. And then since 2012, essentially, ever since the AlexNet appeared, then deep learning has become really popular. So that is very different from all the previous techniques, because now we just pass the whole image to the network and let the network to tell you what are the features. And then you wouldn't really need to design any type of texture descriptors anymore. So it all becomes automated. But there are many, many different types of deep learning structures. So if you do want to study that, there are too many things to read. And so all methods are widely used in current studies. So even if those very early ones, they are still in use. And they are very useful in some applications. So if you do work on some computer vision applications, I do suggest you just try different ways of doing this, all those feature extractions. And surprisingly, in many cases, you might find the really simple ones work really well. And these two, the feature encoding and deep learning, are learning-based, but the other two are not. And texture classification is still a difficult problem, as I explained before. So let's start with a very simple texture representation technique. So that is called the hierarchic features. So hierarchic features it's not just one type of feature. It has lots of the terms that actually quite statistical about these images. So if you consider an image as a matrix, then you can compute all those kind of values based on the matrix. So for example, you can compute what's the entropy in the matrix and what's the sum of variance and some other like correlation coefficient. So it's all linear algebra, and you can compute all this information from this matrix, and that becomes a representation of the feature that's encoded in the image. So that is called hierarchic feature. And also, many of the time, you wouldn't want to compute the hierarchic feature from the image itself. You might just first filter this image using wavelet, for example. Or you can use Gabor filters, or use other kind of transformation technique to get another representation of the image, and then from that you can compute the hierarchic features. So there are many ways of using it. And so even now, some journal paper published in this year is still using this technique, and it's especially useful for medical images. And this one is MRI. So it's especially useful for medical images because many of the studies are done for the doctors, and the doctors prefer to have some understanding about why the computer has interpreted these images in this way. So they want something that's interpretable by them, something semantically meaningful. And then these morphological features become very useful because you can actually describe those features in words, not just a long vector down to the doctor, and they can't really tell what these numbers mean. So hierarchic features are still very useful. And the simple way is you can just extract these hierarchic features and append with some other features, for example, histogram features. That's all very basic features. And then you can do another step of feature selection. That means you want to choose which features are actually useful for this kind of classification problem. So that will involve some other techniques using the feature selection. And once the useful features are selected, then you will generate a pretty condensed version, pretty short vector for each image to represent the whole image. So that's the features. And then once you have this condensed version of features, you can just use even the k-nearest neighbor to do the classification. So it works pretty well. And then let's move on to the second type of features, the higher dimensional features. So I just want to highlight SIFT here because I don't know whether any of you knows it, but if you ever do computer vision studies, I hope everyone will know SIFT. It's just very famous and it's very useful. You can use it pretty much for any type of images, for any type of applications. And even if you do deep learning, you might want to combine deep learning with SIFT. It's just it's a very elegant way of representing the images. So, but it's actually quite complicated. So I will just go into very general understanding of this feature descriptor. So it's essentially about the gradients in the images. So gradients is the same as you've considered the image as a matrix. So when you consider the difference between nearby pixels, there will be a change within the intensity between the nearby pixels. And the rate of change becomes the gradient. So when they change really large, then you get a larger gradient, for example. So at the edge of the, for example, if you take a photo, it has some kind of objects in the photo, then the edge of the object will have large gradient. So that's how you detect the edges. So a SIFT is essentially a way of encoding the edge features in the whole image. So, and then you want to detect the change and also the angle of these, the major gradients along certain pixels. So for example, you can just divide this whole image into different regions. So just do a simple grid kind of subdivision of the image, and then for each region, you just compute what's the gradient within that region. And then the arrow here, the direction, means along which direction you can get the maximum gradient in that region. So then once you have all those gradients and the directions, you can sum. So for example, in this image, they just partition it into 4 cells. So then within each cell, you just want to sum how many arrows are pointing to, for example, this 180-degree direction, and how many arrows are pointing to near to the 45-degree directions. So you just count the number of arrows along different directions. And then you would have something like a histogram of these gradients. And then once you have these histograms of different cells, then you can combine these histograms into a higher level representation about this region. So that becomes a K-point descriptor. That's a SIFT descriptor, and it will be 128 dimensions. So 128 dimensions means you have a vector that has 128 elements in the vector. So that's very brief view of SIFT. Is actually much more complicated. But I just want you to understand is essentially about gradients and some histogram computation about these gradients. So, so when you apply SIFT to an image, you wouldn't just get one single descriptor. So it will be many descriptors, and one descriptor is for one K-point. So a K-point means it has a pretty significant texture feature at that point that you wouldn't want to ignore. So for example, you can just compute SIFT features for each individual pixel of this image. But many of those pixels will give you repetitive features or very meaningless features along these pixels. So you would want to select important points within this image, and then for those points, you get these SIFT descriptors. So that's a way of understanding what K-point is. So in this image, you'll get this set of K-points, and for each K-point, you get this SIFT descriptor. And then one useful way of using it is if you have 2 images, you can compute the SIFT descriptors for each of them. And so, for example, this image, you get this set of descriptors, and this one, this. And then you can just do a matching between each pair of key point, and then find what's the best alignment. So it's like a combination problem. What is the best combination of alignment between these 2 sets of key points? And then once you establish the alignment, you can see whether these 2 images belong to the same scene, or whether it's a rotated version of certain scene. So some example images like that, example applications. So that is called image matching. So it's actually a separate topic from texture classification. So when we actually do texture classification, so for example, for this image, if you do the SIFT feature extraction, you would get lots of K points, and for each K point, you get zip descriptor. So that's not ideal for texture classification because we just want one single descriptor for each image. We don't really want a set of descriptors. So that doesn't really work. So how do we just reduce the set of zip descriptors into a single descriptor for the whole image? Then that becomes the feature encoding problem. So by feature encoding, we mean we want to integrate the local features of an image into a global vector to represent the whole image. So the local features refer to the set of zipped K-point descriptors. And then from this set of local features, we want to just integrate them into a single vector to represent the whole image. So, so the representation here is we got this many, the dot, 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 here, this many of local descriptors, and we want to combine them into another representation for the whole image. So that is feature encoding. So how to do feature encoding? The most popular method is the bag of words. So, so if you ever do like natural language processing, it's a very important concept in natural language processing. It's about if you have a text, an essay, then the essay is composed of so many words, and then if you just want to get overall representation of the text, you can just count the number of words, number of occurrences of the different words in the text. So if there's 10, if you write lots of I in the text, then the number of I's become one element in the feature, and then you just append all the number of words into a vector that becomes a histogram representation of the text, and that is called the bag of words. So for images, it's the same. We want to, based on the local features, we can generate a set of vocabulary from these features. And then from the vocabulary and the local features, we can generate a histogram representation of the feature, the local features. And then that histogram representation is the backwards feature of the whole image. And then we use that back-of-words feature as the input data to the machine learning model. To, for example, the most commonly used one is SVM. You can train SVM to do classification of these images, and then the rest is the same as the handwritten digital recognition. So how do we do the back-of-words encoding? So this is an image. So for example, if you use zipped features, we can get this number of K points along the edges of the image. And then those become all the local features, many of them. And then we can just do a clustering operation on this set of local features. For example, so I will describe what clustering is, but consider if we cluster them into 5 different clusters, then these 5 different clusters, the center of the clusters becomes the vocabulary representation of this data set. And then you can use, so that vocabulary is essentially the same as the words that you can see in your dictionary. So that means the possible occurrences of feature descriptors that you can get from an image. And then based on this vocabulary, you can just match which other match the local features with the vocabulary, and then you can get a histogram representation. So let's go into the K-means clustering first. So the clustering here, normally we use K-means clustering. It's just the simplest way of doing clustering. So K-means means you want to generate K number of clusters, and based on them, the mean operation between the data. So if you consider this example here, it's an iterative process, the k-means. It starts with random initialization of clusters. And then once with the random initialization, you get the center of the clusters. And then you just compute the Euclidean distance between each data point to the center. And then you just assign the data that is closest to this cluster to this cluster. So we just partition the data based on the distances between the data and the cluster center and partition them into different clusters. And because once you partition them into, for example, 3 clusters, then the mean of the data in one cluster changes from the initial mean that you have assigned randomly. Then once that changed, you just update the mean of the cluster, and then based on the new means of the cluster, you do another round of distance computation and the cluster assignment. So it becomes an iterative process. And then finally, hopefully, you will be able to cluster these images into some meaningful clusters. So it will hopefully represent how we human beings would consider which data actually belong to the same cluster. But because this one is two-dimensional representation, you can still see which data belong to the same cluster, hopefully. But once you get very high-dimensional data, because, for example, the safe data is 128 dimensions, you can't really visualize which data are actually close to each other. So when you use k-means, you just trust what k-means can do. Can't really tell whether it works really well. So with those clustering technique, we get these clusters, and each cluster the center of the cluster becomes the vocabulary. And then with those vocabulary, you can do another set of Euclidean distance computation. For example, for this safe descriptor, you want to see which cluster is closest to. So if it's closest to cluster 2, then we say there's one data belong to cluster 2, the vocabulary 2. So in this way, we count the number of points belong to each cluster for all the points. And then we get this histogram for this image. And then that histogram becomes, you just put the numbers here, then that becomes a feature vector. So that is the backwards representation of the image. And so once we have these backwards feature vectors for the training images, then we can just train and classify. So for example, you can use KNN or SVM or even decision trees or even neural networks to do this classification. So just a recap. So with backwards, it does involve learning because the k-means clustering is a learning-based approach. It works on the set of training data that's given to generate the vocabularies. And so the step is we want to extract a set of local features, and then we use k-means clustering to generate the visual words. And we assign local descriptors to the nearest visual word, and then count the number of occurrences of the visual words and obtain the histogram feature representation. So that histogram representation becomes the backward representation. But there are lots of limitations with backwards. For example, if you consider k-means clustering, it's a very simple clustering method. It does work well in many cases, but it's not optimal. So that is one limitation. And another one is in this model, when you assign the local features to the vocabularies or the visual words, you just assign one feature to one word. So there's no like a soft assignment or some probability computation within this assignment. It's just a direct binary assignment. We want to introduce some probabilities in this process to make it more robust. So that comes another very powerful model that is called feature vector representation, feature vector encoding. And it's a bit more complicated. So I'm not going into the actual detail. I just want to let you know there's this kind of method in case later you want to do your honors year project or something. It's based on the Gaussian mixture model. So Gaussian mixture model is about you want to do the cluster, but also you want to see, besides the mean, you want to see what's the variance within the clusters, some kind of additional information, statistical information. And then you, based on this Gaussian modes, it's called modes, and then you can do a soft assignment. So soft assignment means you're not just assigning a local feature to an individual real world. Now you are doing combined assignment among all the real worlds. So there will be a probability assignment. So if this local feature is more likely to represent a certain type of cluster, then you assign a higher weightage, something like that. And then based on this, you compute the first and second order distances. And then the first and second order distances can be combined together to represent the whole final feature vector encoding representation. So this approach gives you a very high dimensional feature representation, and typically it can be 64K elements in one vector. So if you consider an image, it might not be very large, but the feature vector representation can be even larger than the image. So because it's very high dimensional, and then the choice of machine learning model is now quite limited. It wouldn't work really well with k-means because KNN, because KNN is just direct distance computation. But it works really well with SVM classifier. And SVM had this ability to handle really high dimensional vectors even when you are limited by the number of images or the number of training data. So normally, if you use feature vector, you would definitely want to use SVM classifier. And if you want to do something more advanced, you will have to benchmark with how SVM works with this kind of model. And it works, this kind of technique works really well with texture classification. And if you take a look at this paper, and the performance, in many cases, it can be even higher than deep learning, even nowadays. So, yeah, I just want to move on to talk a little bit more about deep learning. There is another deep learning course. I think it's also done by Alan, if you are interested. He will talk a lot more about the fundamental theories or all the different components in a deep learning network. So here, I just want to show you some cases when you actually do deep learning for texture classification. The texture classification problem would not really work well with very standard convolutional neural networks. So if you just use convolutional neural networks, it gives you much lower performance than using the feature vector with SVM approach. So there are some other people trying to use convolutional neural networks, and then they develop this, for example, TCNN and BCNN architectures. So essentially, they want to make the network capable of handling more ambiguities in the data. So they add more concurrent path in the network. But they actually still don't work really well. But there are some development along this path. So another way is something works the best now is we can combine feature vector encoding with deep learning. So that means, for example, if you consider a deep learning network, it has multiple layers of convolutional layers, and then some layers of fully connected layers. So if we just truncate this network, we just take the first few convolutional layers, and we get feature from the final convolutional layers, and then we can treat them as a set of local features similar to the sift features. Meaning we can just use them to replace the sift features that we can get with sift feature encoding. And then we just put those convolutional features through a feature vector encoding. And then we get this really long 64K dimensional representation of the image. And then you can just use SVM to do the classification. So that one will give you a very good result, much better than the previous convolutional neural network, even though they are optimized for texture representation. And then in this work, we can also include some other dimensionality reduction technique to further optimize it. So then you will get a pretty good classification result. But I think now for texture classification, the best you can get is around 80%. So it's still not very good. And then the other one is, this one is a pretty interesting concept. I just want to show you that you can actually consider deep learning and feature encoding as essentially the same kind of model. Because so the first two rows about feature encoding, so you can extract, for example, you can extract sift features or other type of features, and then you do the encoding and you get the histogram representation, and then do a classification. So that's the standard way of doing it. And with deep learning, it's actually very similar. You can use convolutional layers to get those local features, and then you get those local features, and normally you need to do some kind of pooling operation. For example, average pooling or maximum pooling. And then you get some other feature maps. And then this kind of feature map is similar to what you get with backwards encoding. And then in convolutional neural networks, you would have some numbers of fully connected layers followed by a loss layer. So that will be the same type of model as a classifier. So essentially, these two type of models can be unified into one single concept. And then that also tells you can actually mix and match them to derive some more advanced models. So another application for this one is for medical images, for texture classification. So these are the CT images. So N is for lung diseases. So nowadays, most of the cases, if some patient has a lung problem, they will do a CT scan. And one of the very common diseases is called interstitial lung disease. And it's a type of disease that actually consists of more than 150 disorders of the lung parenchyma. And I'm just showing you a few examples here that are the most common types of ILDs. And for example, emphysema, you definitely should have heard of it, and fibrosis. These are very common disease in the lung, but it's often quite difficult to separate them, to identify the exact subtype of this disease. So there's some demand among the doctors to have some computer-assisted approach to do this automated detection of the different types. But the difficulty here is the same as I introduced at the start. There are very high intra-class variation and inter-class ambiguity here. So it means if you consider the emphysema, these are the two cases of emphysema, but they look very different. And also for ground glass or fibrosis, they all look, even for the same class, with different patients, they can look very different. So that is the intra-class variation. That's the most significant problem in any type of medical images, essentially. And then there's also inter-class ambiguity. For example, these micronodules can look very similar to the normal cases. Or emphysema or the ground glass can look similar to the micronodules as well. So that is called interclass ambiguity. So how do we solve these problems? And many approaches have been developed. So it starts from very simple filter-based texture representations to the later deep learning approaches. Many approaches have been developed. And so I just want to show you one case, one study last year about how they can actually integrate medical knowledge into the deep learning framework. So it's different from any other applications. So most of the time, when you consider nowadays the deep learning studies, they would want to do a fully automatic approach with just deep learning and not any other type of algorithms. But in medical images, on the contrary, we do really want to integrate some medical knowledges. And that helps a lot with the whole flow of the algorithm. And so in this case, it's actually quite simple approach because there's some unique properties with CT. And with CT, you will get different attenuation with different tissues in your body. So if you consider the difference in the attenuation, you can do a rough partition of the tissues and do a different filtering of those different attenuation scales to some simple image processing. And in that approach, you are actually encoding some medical specific knowledge into the algorithm. And then once you do that, you can do some resampling and multi-scale processing with these images. And then you do this deep learning classification. And in this way, this study actually gave a pretty good improvement over the previous approaches. So in summary, texture classification is an important and fundamental problem in many applications. So not just medical images. So consider the previous example about urban planning or just general texture classification for even social media images. And the methods have evolved from morphological representation to deep learning. But classification accuracy is still quite low in many cases. So if you want to study this kind of problems, the same type of design choices need to be considered, especially about feature representation and classifier. And some standard evaluation metrics can be applied. So for further reading, this paper actually used quite a number of images from this paper in this lecture. So you can just take a look. It's a review paper, so it basically contains everything, almost everything in this field over the past 2 decades. And you can also download some very useful toolkits. So this one is using MATLAB. So if you are able to use MATLAB, many of the image processing techniques can be used very easily. And this toolkit also comes with very good tutorials, give you very good, a brief understanding about all those type of algorithms, and some other classifier model for you to just have a brief understanding. Okay, and this is another one because I really like this Fisher vector method, and it has lots of applications, not just texture. Even for face recognition, you can use Fisher vector representation. So if you're interested, you can have a look at this paper as well. Okay. I think we just go straight into the third part. So the third part is about AI in biomedical imaging. This part is much shorter than the previous one. I think I just want to give you a few more case studies about how we can use machine learning in computer vision. So in this part, I'll talk about why do we need biomedical images and why do we need AI for it, and is there any particular challenges in this type of studies, and how do we address these challenges? So I'm not sure whether any of you know about precision medicine. It's a very hot topic right now. So anybody working in medicine would know about precision medicine. So that means the doctors want to design a personalized approach to treat the patients. So for example, if you get fever, maybe you wouldn't just get Panadol for every one of you. They would want to have a more personalized approach to do the treatment. So it's not just a textbook check of what are the symptoms and then what are the corresponding treatments, but it will be more focused on your individual history and your personal characteristics. So that essentially is what precision medicine is. So now with precision medicine, the most fundamental enabling factor is now we can do genomic study because now if you just sequence the gene in your body, it's quite low cost already. You can get pretty long sequencing and pretty easily, and then lots of disease can be diagnosed from the gene. Even the cancer can be studied from the gene level rather than, for example, medical imaging. But in many cases, images are still very useful because even for cancer, you might not really show a genetic mutation of certain kind. It might be just overall malfunction of certain tissues, for example. So those will be still visualized using medical images. And especially, you wouldn't want to do a biopsy for anything. You still want to start with CT, MRI, because they are painless and not invasive. So images are very useful. And so the whole flow that integrates images and data and gene and even proteomics is called systems biology. So that will be something you might heard of. So we want to use AI in biomedical images because biomedical services and research produce lots of imaging data. And these imaging data can be quite large. So for example, if you remember the whole slide images, they can be actually gigapixels per image. And if the doctors need to process 100 patients every day, then that's too many data they need to handle. So with big data, analysis becomes a huge problem. And AI is essential in achieving automated, effective, and reproducible analysis of biomedical imaging data. So the most important thing here is reproducible, because doctors can have different opinions. But with computers, once you have this program, it will always do what this program do. So it's very standard and very reproducible. And so that's a main attractive point of using imaging, AI imaging. And there are, however, many unique challenges with biomedical images compared to general non-medical images. So I will go into that later. And now companies such as GE, Siemens, and Google invest heavily in AI-based biomedical imaging applications. So this is the same example for the texture classification. So if you want to do cancer detection, deep learning, especially in this case, deep learning is becoming very popular. So I want to talk a bit more about whole slide images here. So whole slide image is very high dimensional resolution, very high resolution images. So it can contain gigapixels or even 10 gigapixels in one single image. Because remember, you can just keep zooming in the image and get very detailed view of the cell level information. So it's a trade-off between how much information you can get from these images, but also what's the complexity of analyzing these images. And now there's a shift of trend to get fully digital environment for pathology. So it's not just seeing under the microscope, but there will be more digital processing with these images. So that's the same example. So how Google actually process these images is a very simple deep learning framework. First of all, they have a set of training images. So because they are Google, they can get lots of images from the other hospitals. And the images will come with ground truth annotation. So it means some pathologists would annotate which regions in the images represent cancers and which regions do not. So you get very detailed region-level annotation along these images. Then once you get the images and this ground truth, then you can just partition the image in the very big image into small patches. And so, for example, in this case, you get this 32 micrometer times 32 micrometer patches, and then you get thousands or millions of patches, and then you put all these patches into the deep learning neural network, and then just do the training. The ground truth means 0 or 1. 0 means it's not cancer. 1 means it's cancer. Then you just let this neural network train and try to get good classification result. And then once you get this trained model, then just apply the model onto the test image, patch by patch, and then you'll get this patch level output on this image. So, for example, they might detect this region as the cancerous region, then that will be the output. So that is a very simple approach, but in reality, most studies, especially with smaller companies, they wouldn't have images provided with patch level information, patch level labels, because to get pathologists to annotate those patch level labels is not really realistic. It requires too much work for them. So, so what you want to do is actually you want to get this image, and you might get some image level information like whether this patient does have cancer or he doesn't. So with this image level information and the whole image, you just want to design a system that is able to do this classification without the patch level ground truth labels. So that is one of the main real challenges that's faced by all the researchers. And then the second challenge is the standard challenge with any texture classification problem. So you get lots of heterogeneity, means the intra-class variation and inter-class ambiguity in the images, and how you can actually handle these problems. So, so there's one pretty simple yet very effective approach. It's a clustering-based approach. So consider this is a very large image. It's just showing as very small thumbnail, but actually it's very large, tens of gigapixels. And then you want to divide these images into patches. So for example, one patch might be 1K by 1K pixels in one patch. Then once you have all the patches, you can just extract the features. For example, you can use the filtering-based approach with the hierarchic features to get all the patch level features. And then you get these thousands of features of the patches, and then you just do a clustering. So a k-means clustering will be sufficient. So you just cluster all these patches into, for example, 10 clusters. And each cluster would contain, ideally, they would contain patches of similar appearances. So, and then with these 10 clusters, you can find what's the center of the clusters. And then for each center, you just identify a single patch that's closest to the center of the cluster. So in the end, you would identify just 10 patches from this whole image. And then for each of the 10 patches, you do another level of feature extraction, maybe more detailed like cell level features. And then with these features, just do another level of classification. Can train, in this method, use elastic net classification. So it's similar to a linear regression model. So just do a classification of all the identified patches, and then do just assign the 0 or 1 label to these patches, and then do a majority voting among these patches. Then they would identify whether this image represents a cancer or not cancer. So there's another view of so the 10 patches assigned, and then based on the 10 patches, just do a classification. So this method, not very complicated, but it works really well. So for example, this one is two-class classification of brain tumors. So if you have a brain tumor, it can be the most popular types are GBM and LGG. So, but they require different treatment, and they will have different outcomes. So the doctors will be interested to know what's the exact type of this brain tumor. So if you classify these two types with this method, you can get very accurate result. So this table means if it's actually a GBM, then this method gives you, so if 170 are GBM and this method gives you 170, but there's another 12 GBM, but this method gives you LGG. So the error rate here is just 12 over 170. Or if you consider recall, then it's 170 divided by 182. So that is a recall. So it's very high. And precision is this 179 altogether detected as GBM, but only 170 of them are actually GBM. So then the precision is 170 divided by 179. So both recall and precision are very accurate. And so it's a very good non-deep learning based approach. And then there's another approach with deep learning. So we have to use a patch-based CNN because the whole image is too big. You can't just dump the whole image into a deep learning model. It wouldn't work. So it still has to be a patch-based. But now you don't have the patch level labels anymore. So you can't just use what Google does to have the ground truth labels corresponding to all the patches to train the deep learning model. So there has to be some other ways. And one way is just to expectation maximization approach. I guess you wouldn't know about that. It essentially means an iterative approach. So it has a expectation step and maximization step. So it means it's similar to a k-means clustering. You start with using all the patches to train the network and just use the image level label as the patch level label. And once the network is trained, you just, based on the classification output, you want to just do another way of trimming these patches to say whether some patch are actually discriminative, meaning they are useful in this classification process, and some are non-discriminative, meaning they are not really useful. They might be just background or just normal tissues. They doesn't really represent any specific information of the type of tumor. Then based on this trimming, you just do another labeling of all those patches to refine the ground truth labels and do another iteration of training. So then just update these patch labels again and do another iteration. So it's an iterative approach, and finally you would get this the patch level labels. And then you can assemble this patch level label into a histogram. And then use, for example, SVM to do classification of this histogram. And then you will get this image level classification result. So this image shows you some patches that have been identified as discriminative in these images. So those red or green patches are those finally kept in the training process that's deemed as discriminative. So with 32 images, we can get about 84% accuracy. So if you just use CNN to get features and use SVM to do the classification, that will give you only 62% accuracy. But with this iterative approach, you can increase it to about 84. So there are lots of studies in this area. I just want to show you how you can just use Google Scholar to do a search. I don't know any of you if you know. So if you want to search about scientific work, don't just do Google search. We would want to use Google Scholar because that will actually give you all those scientific references. And so you just go to scholar.google.com and then you just type in the keywords. And there are some other options, like you can choose since which year this data are published, and some other choices. And then you will get those references for you to study. So in summary, biomedical imaging is critical in precision medicine, and there are unique challenges when analyzing biomedical images, especially with insufficient ground truth. So consider in this microscopic image example, insufficient ground truth means we don't have the patch level labels. If we do have it, then we can just do a very simple deep learning training. But most of the time, it's not the real case. And also, we have highly heterogeneous data. That's a very common problem with all medical images. So it's a very active area in both industry and research. And so that's all. I hope you find it interesting. And if you have any questions, you can either email Ellen or me. Or if you have questions, you can ask now. Okay. I think we have early finish with this lecture. Thanks.